Hello. In the past few days, we have learned how to solve an LPP, how to formulate it, but just by using the graphical method. A graphical method works only when there are two variables in an LPP. But what we will start doing today is basically the techniques that we will need to solve an LPP when there are more than two variables. It is called the simplex method, which will be dealt with in another video. But in this video, what we will discuss is something that is required for the simplex method to work. Okay, so let us just start things with the basic variables and solution. Okay, so let us start. Basic variables and basic solution. Okay, so let's see. Let there be an equation ax equal b. Okay, so we have seen this equation where A is an m by n matrix. Okay, why are we studying all this? Because as you remember, the constraints of an LPP can always be transformed into an equation that looks like this, where A is a matrix, X is a vector consisting of the variables, and B, it is from the constraints only. Okay, so where A is an m by n matrix of rank m. So over here, if you are expanding this equation, how will it look like? Okay, if you expand it, you will have something that looks like this: a11 plus a12 a12x2 plus we will be having n columns, so a1n xn equal b1. Okay, similarly a21x1. Okay, this is not required, but I'm just writing it anyway. Okay, so that you will clearly see what is happening. And a m1 x1 plus a m2 x2. So if you expand this one, you will be having something that looks like this, bm. Alright, so now if you are taking a look over here, how many equations are we having? We are having m equations. And how many variables are we having? We are having n variables. So basically over here what we will do is, okay, there can be three cases where n is greater than m, n is equal to m, or m is greater than n. Okay, but over here it is better, okay, if we discuss the first case first, okay, which is the number of variables is greater than the number of equations. Okay, so over here, okay, and n is greater than m. So over here, what can we do? We can set n minus m variables to be equal to 0. Okay, do not worry. Again, when we are doing the examples, you will understand better. So set n minus m variables to be equal to 0. Okay, then what will we be left with? Okay, the remaining variables, these, okay, maybe I should write like this. These n minus m variables are called the non-basic variables, whereas the remaining m variables are called the basic variables. Okay, so this is the definition for basic variables. Okay, but what is a basic solution? Okay, the basic solution is basically the value of the basic variables, okay, on solving the equation after setting the n minus m variables to be equal to 0. Okay, the values, okay, of the basic variables. I'm just writing on solving the equation after setting the n minus m variables equal to 0. Okay, do not worry, when we are doing the examples, all these things will be cleared up. Okay, and then you can just refer again to the definition. Okay, so this is basically what are basic variables and what is a basic solution. Okay, it can work for any equation which can be written like this: ax equal to b. So now, okay, I will just go on ahead and define what is a degenerate solution. Actually, over here, whenever we are saying a basic solution, okay, it will be of this form. Okay, it will be a vector. Okay, it will be a vector consisting. It will be a vector consisting of the values. Okay, so this whole thing is called a solution. Okay, maybe I will write something like this: a vector containing the values. Vector containing the values of the basic variables. Okay, so I think I will define it in this way. Okay, degenerate solution, I will define it like this: if one of the coordinates if one of the values in a basic solution is 0, then that basic solution is degenerate. Okay, so this is our definition, and also I will define something else, which is called as the cos vector. Okay, the cos vector, if you remember, an LPP always has an objective function. Okay, an objective function will be maximize z equal to cx. That the objective function of an LPP be maximize z. Over here I'm writing maximize because even a minimization problem can be converted into a maximization problem. Okay, so I'm defining it for maximization, equal to c1x1 plus c2x2 plus cnxn. Or in matrix form, this one can be written, okay, in matrix form it can be written as C transpose X. Okay, so let this one be the cos, the objective function. Then the vector CB, then the vector CB, okay, equal C, okay, I will write over here B1, CB2, CB M, where CBI, okay, CBI, or CB1, CB2, CBM are the coefficients are the coefficients of the basic variables in the objective function. Okay, then this vector is the cos vector. Okay, so basically what we are saying over here is sometimes maybe x1 and x2, they are the basic variables. So the cos vector will be c1, c2. Sometimes c1, c2, c5. Okay, if x1, x2, x5, if x1, x2, x5 are the basic variables, then c1, c2, c5 will be the cos vector. Okay, I hope that is clear. Okay, so you can only find the cos vector after finding the basic variables, but it is related to the coefficients of the objective function of the LPP. Okay, so with that being said, let us just do some exercises. Okay, so let's try the first exercise. Okay, question is, find a basic solution of the equations. Okay, I'm just writing over here 6x2 plus 2x3 plus x4. Okay, 6x1 plus 4x3 plus 6x4 equal to 2. Okay, so over here, if you are noticing the question, it is saying a basic solution. Why are we using the word a? It is because actually there we can find so many basic solutions, okay, depending on our choice, as you will see. Okay, so over here, how many equations do we have? We are having two equations. Okay, so m is equal to 2. What is n? N is the number of variables. We are having 4 variables. N is equal to 4. Okay, so we can choose. Now n minus m will be equal to 2. Okay, so how many non-basic variables can we choose? We can choose 2 non-basic variables. Okay, maybe you can write this one. You can choose 2 non-basic variables. Okay, these non-basic variables, you can choose them to be anything. Okay, you can choose x1 or x2. Again, it depends on your choice. Okay, so let us just choose x3 and x4. Okay, similarly, you can choose x2 and x4. It doesn't matter. It really depends on your choice. Okay, maybe say x3 and x4. Okay, so x3 and x4, they are the non-basic variables. So their values will always be equal to 0 because non-basic variables will always be equal to 0. Therefore, x3 equal x4 will be equal to 0. Okay, hence, okay, the remaining variables which is x1 and x2 are the basic variables. Okay, so these are the basic variables. Okay, so now, but we have to find the basic solution. We have got what are the basic variables. Now we just need to find the basic solution. Okay, so substitute x3 and x4 equal to 0. Now the equations transform to if you put x3 and x4 equal to 0 over here, you will be having 2x1 plus 6x2 equal to 3 and 6x1 plus 4x2 equal to 2. Okay, so now we can solve this because now we are having two equations and 2 variables. So we can easily solve this one by any method that you like. Okay, so we can multiply this one by 3. Okay, times 3 and leave this one as it is. We have, okay, maybe I'll just rename this one as equation 1. and this one as equation 2. Multiplying equation 1 by 3, we have 6x1 plus 3, 6, 18, 18x2 equal 9, and this one remains as it is, 4x2 equal to 2. Okay, so now we can easily solve this one. Okay, we can subtract them. So we will be getting 18 minus 4 will give you 14, 14x2, 9 minus 2 will give you 7. So therefore x2, it will be equal to 1 upon 2. So x2 will be equal to 1 upon 2. And similarly, we can find out x1. So from equation 1, substitute this x2 in equation 1, we will be having 2x1 plus 6 times x2 will be equal to 3, equal to 3. So x1 will be equal to 0. Okay, so x1 will be equal to 0 and x2 will be equal to 2. Okay, so now we have found the values of the basic variables. So this is the basic solution. Therefore a basic solution is x1 is 0 and x2 is equal to 1 by 2. Okay, just a follow-up question for this is the basic solution degenerate? Okay, a follow-up question is this: is a basic solution obtained in the above? It's a basic solution above degenerate? The answer will be yes. Yes, it is a degenerate basic solution because one of the values is 0. Yes, because x1 is equal to 0. Okay, so if one or more than one of the values in the basic solution is 0, then that solution will be a degenerate solution. Okay, so again a follow-up question. Okay, let an LPP be, okay, maybe maximize z equal 2x1 plus 3x2 minus 7x3 plus 7x4 subject to, okay, again the constraints now they are the same thing, okay, just like we did in the previous problem, which is 2x3 plus x4 equal to 3, 6x1 plus 4x2 plus 4x3 plus 6x4 equal to 2. x1, x2, x3 and x4, they are all greater or equal to 0. Okay, so over here what I want is find a cost vector. Okay, again, find a cost vector. Okay, so if you have to find a cost vector, again you are using the word because there can be so many cost vectors depending upon the basic variables. So just like we did, okay, we have found that x3 and x4 are basic variables. Okay, that is x1 and x2 are basic variables. Solution, as in the solution above. Okay, the first part that we were doing, x1 and x2 can be chosen to be the basic variables, hence cost vector. The cost vector will be the coefficients in the objective function of x1 and x2, which is 2 and 3. Okay, so hence the cost vector. Hence the cost vector is CB equal to 3. Okay, I hope it is clear. That is enough for now. Okay, We will also be doing more problems based on basic solutions when we are doing the simplex method in the next class.